Now, the pH scale may sound rather random in that why the heck would we pick a scale from 0 to 14? Like, why wouldn't we just use 1 to 15? That would make a lot more sense, right? But no, 0 to 14. Well, there's a mathematical reason behind that, and you're about to see why that is. First, I want to tell you about, again, our good old friend water. Again, water, I often tell you guys, is the same thing as hydrogen hydroxide, or basically H2O is the same thing as HOH. So we have the H of the acid and we have the OH of the base, and it's a 1-to-1 ratio of H acid, OH base. So it is a neutral compound. It's a even distribution of H plus concentration and the OH minus concentration. Again, that's why it's a neutral solution. So what you guys can see right here again is what I just basically described. If we have water, it can ionize into H and OH, which of course is the same thing as, like I just said, HOH or water. Here again is another way to show the exact same thing. If we have 2 moles of water, then what we really make is a hydronium ion and our hydroxide ion. These basically are the same thing. We have an H here, but notice again, we have an extra H. So like I said, it is basically the exact same thing for both of them. Again, that is the ionization of water. So when we have a glass of water in our hand, it is not 100% always H2O. At any moment, there will be some molecules of water that will be splitting into a hydronium and a hydroxide. Then they may reform back into water, but that's why the arrow is going both directions, because it's going to be an equilibrium, a state somewhere in the middle where the net will be mostly, of course, towards the H2O and a little bit of the hydronium and hydroxide. Again, it's going to be ionizing constantly, but also the majority of the time will stay as an H2O molecule. Now, all that being said, on the next thing on your screen, we have the concentration of H plus ions. Remember, a bracket like this represents a concentration. So the concentration of H plus ions, we measure in molarity. Remember, molarity is moles over liters. Well, guess what? There's moles over liters. So if we have 1 mole of H plus ions in exactly 1 times 10 to the 7 liters, then what we end up with is a molarity of 1 times 10 to the negative 7 H plus ions. Same thing over here. If I have a concentration of OH minus, which is 1 mole of OH minus over 1 times 10 to the 7th liters of water, what we end up with is 1 times 10 to the negative 7 molar of hydroxide. As you guys can see right here, excuse me, if I multiply my concentration of H plus ions and my concentration of OH minus, which would basically be this multiplied by this, that'd be 1 times 10, and then you add the exponents. So negative 7 plus a negative 7 gives me a negative 14. And that, my friends, is why we use the 0 to the 14 scale. It's all based on the molarity or the concentration of H plus ions and OH minus ions in solution. So knowing this equation, again, this right here is given to you on the formula chart. So you have this equation provided to you. It says determine the hydrogen ion and hydroxide ion concentrations in 1.00 times 10 to the negative 4 molar hydrochloric acid solution. So what we need to do is we need to realize this equation tells us that 1 times 10 to the negative 14 equals my concentration of H plus ions. Notice this is an acid, so this is my H plus, which would be 1.00 times 10 to the negative 4 molar HCl times my concentration of OH minus, which I don't have. Why don't I have it? Because again, what they gave us, this right here, is for the acid, the HCl. Again, remember, H in the front means an acid. Therefore, what we don't know is our hydroxide. So that's what we're going to solve for first. Excuse me, guys. So mathematically speaking, or algebraically speaking, I should say, you guys know that if I need to get this away from the OH, leaving OH minus all by itself, I'm going to divide this side by what is next to my OH, or my X, if you will. And if I do it to this side, I've got to do it to the other side as well. You guys know how algebra works. Okay, so I'm going to cancel that out. Finally, my OH concentration is going to equal 1 times 10 to the negative 14 divided by 1.00 times 10 to the negative 4. So let me type that in. 1 second E negative 14 divided by 1 second E times 10 to the negative 4. And what I get is 1 times 10 to the negative 10. Again, not surprising if I have a division problem like this. You would multiply or divide the two numbers in the front. 1 divided by 1 is, of course, 1. And then I would subtract the exponents. So negative 14 minus a negative 4, that's a double negative. So that's basically minus 14 plus 4 gives me 1 times 10 to the negative 10. So that is my OH concentration. So we got the hydroxide. They also want the hydrogen ion. Well, guess what? This is the hydrogen ion concentration right here. Why? Because again, it is the acid. They gave us the concentration of acid. Therefore, that is the hydrogen ion concentration. Notice there's only one H. That would not be the case, say, if we were going to do H3PO4. If we were going to do phosphoric acid, that 3 hydrogens would change the equation a little bit because that's 3 times as many hydrogens, whereas HCl only has 1 H. So therefore, the number they gave us is the hydrogen ion concentration for our solution of hydrochloric acid. So we have an answer here for the hydroxide. I'm going to go ahead and put it in red. We have the answer right here for hydroxide, and then we have the answer right here for our hydrogen H plus concentration. So that's how we're going to do number 1. Number 2 is going to be very similar. So it says determine again the hydrogen ion and hydroxide ion concentrations in a solution that is 2.50 times 10 to the negative 3 molar NaOH. Now notice again, OH, that is our base, that's sodium hydroxide. So therefore, I already know my answer for my hydroxide ion concentration, because there's only one OH in a molecule of NaOH, is exactly what it says it is, 2.50 times 10 to the negative 3 molar. So there's my first answer, just like this was our first answer. Now I'm going to go ahead and do the equation that we had before. So I know that 1 times 10 to the negative 14, 14. Again, what I'm doing is this right here, equals my H plus concentration, which this time we don't know that one, but we do know this because again, they gave us this in the question. And again, there's only one OH in a molecule of NaOH. Therefore, we're just going to use the number as is. Then again, I'm going to divide those numbers. So this will come over here, 2.50 times 10 to the negative 3. That will cancel out, leaving me an H plus, I'm going to put it over here, H plus concentration of, let's see, 1 second E negative 14 divided by 2.50 second E negative 3 equals, my H plus concentration is 4.0 times 10 to the negative 12 molar. All right, guys, there we go. That's how you're going to calculate the concentration of one ion if you're given the concentration of the other ion. Again, as long as there's just one proton in the acid and there is just one hydroxide in the base. And that's all there is really to it.